Now we are in the second day of the conference. Today's event, we have actually two congratulatory speeches from Professor Young Chang-ju of Seoul National University, former Vice Minister of the Ministry of Science and ICT. And also we have a second congratulatory speech from the President Han Kyu-ju of Korea Atomic Energy Research Institute. Okay, so please, Professor Young Chang-ju, welcome him.
Thank you very much. Hello, good morning. My name is Young Chang-ju from Seoul National University, Department of Material Science and Engineering. I'm very delighted to meet you in this morning. We come from the Japan, Korea, and Taiwan, which is a very important three countries in the East Asia. I think it's very important to have such important meeting. I'm also very sorry that I cannot attend yesterday because I was on a conference in Jeju Island, so I just come here to attend this meeting. Actually, the reason I stand up here is that I was Vice Minister for Science and Technology and Innovation at the Korean Ministry of Science and ICT. About 4 months ago, I served as my first Vice Minister for the Yoon Suk-yeol President. I'll briefly introduce my former office was doing, and I hope to briefly introduce that Korea's R&D focus on national focuses. So the STI office, so the Science, Technology and Innovation Office, which I was in charge of, was the overseeing the science and technology policies in Korea. You can say that it is like a CTO of a country. So my STI office has 3 functions. First one is the planning the national R&D policies, and the second one is the deliberating and adjusting the budget for the national R&D investment. And lastly, this is evaluating the outcomes of those R&D national projects. As an office that leads the national STI policies and progresses, the future direction, we make the diverse efforts, especially making the policy on the mission-oriented R&D. The main 2 functions we are doing is that we are planning the 12 national strategic technologies. We select 12 strategic technologies, and we are focusing these technologies. These Korean government 12 national strategic policies is a important technology in the global race for technology dominance and supply chains. The 12 technology includes a semiconductor and display, and rechargeable batteries, advanced mobility, and next generation nuclear power, and advanced biologies, aerospace and ocean engineering, and hydrogen, and cybersecurity, artificial intelligence, and next generation network, and advanced robotics, and quantum technology. I think that each government select similar topics and enhancing them to secure the national R&D, national technologies. I believe that I realized that today and yesterday's conference was focusing on the semiconductor, AI, and energies, which is quite similar, and which is the important part of the 12 national technologies. So I think it's very important meeting. And also, personally, I'm the engineer who is working on the semiconductor. I was involved in interconnect and packaging. So I'm also very happy to see you all in here. Another important focusing on the Korean government's focus is international collaboration. We realize that international collaboration is quite important. So this government pushed a lot of effort to enhance the international collaboration. So in this content, it is quite important that we have the meeting like this and make policies. Think about what direction we should go on. So I'm very happy to come here, and I will listen today's meetings, and also I'll catch up with the yesterday's meetings results, and I also helped to convert and transfer to the government to have a very better progresses in these directions. Okay, thank you very much.
Thank you. The next congratulatory speech will be given by President Han Gyu-ju of Korea Atomic Energy Research Institute. Actually, it was quite surprised that he showed up this today because he didn't notice, any time. So welcome him.
Hello. As he said, this is quite unexpected congratulatory speech. I just learned about this meeting yesterday from Professor Kwon, who gave us talk in the morning session. In fact, I'm a professor of nuclear engineering at Seoul National University, but I'm currently temporarily leave to serve as the president of Korea Atomic Energy Research Institute. About 4 or 5 years ago, the main drive for nuclear energy was the carbon neutrality, but about 2 or 3 years ago, there is an additional need for nuclear energy. That is the national energy security. But from last year, there is another thrust for nuclear energy, which is the increased use of AI and sufficient electricity supply to data centers. I learned yesterday from Professor Kwon that the semiconductor factories need a lot of stable voltage electricity supply. First of all, they need high power laser for example, to make the semiconductor circuit. Also, they need high power electricity for plasma etching, and also for maintaining clean room. There is also a lot of electricity needed. And the most important thing is that stable voltage is quite important. So renewable energy might not serve as a proper electricity supply for semiconductor factories. In contrast, nuclear electricity gives stable and effluent electricity. And in Korea and Taiwan, and also in Japan, there are very large capacity semiconductor factories. I think to supply, to maintain stable electricity, nuclear energy is quite important, quite essential. And people say that renewable 100% is the way to go. But as I said, the important weakness of renewable energy is that it needs a lot of energy storage systems, because sun does not shine always. So renewable energy 100% is not practically or economically possible, but in contrast, carbon-free 100%, including nuclear energy, I think that's the way to go. We can combine renewable energy and nuclear energy to achieve carbon neutrality, and also to meet the increased demand of stable electricity for data centers and semiconductor manufacturing. So please spread that CF100 is the need, is the way to go to your colleagues. And finally, I congratulate for having this very important, significant meeting between the 3 major semiconductor countries in the East Asia, Japan, Taiwan, and Korea. Thank you very much.
Thank you. Now we will begin the energy session, and I will hand over the floor to the Professor Hideki Shiroyama of University of Tokyo, who will moderate this session.
Yeah, thank you very much for your kind introduction. And I'm Hideaki Shiroyama from University of Tokyo. My background is political science and public policy, not necessarily a science technology per se, but I have been working from the interface between the science technology and the public policy, including the renewable or the nuclear safety and so on. So that might be the reason why I will be the moderator today. Yesterday, we had an extensive discussion about the AI or the semiconductor issue. And today, we will focus on the energy. Maybe the topic seems to be a little bit different in that yesterday we were focusing on the component-specific technology rather than the system. Today, we are talking more about the system in the case of the energy. And also, as was mentioned by the president, and the AI and the semiconductor might be the demand side of the energy. But on the other hand, maybe we will mainly talking about the supply side of the energy today. So maybe yesterday's discussion and today's discussion expected to be complementary to each other. Today we have a 3-hour session. So the session is divided mainly into 3 parts. The first part focusing on the renewable energy from the Korea, Taiwan, and Japan. Then the next session is focusing on the nuclear energy, including the SMR. Focusing also on Korea, Taiwan, and Japan. So we have the 15 minutes presentation by each. So that is the first part. The second part begins with the session on the energy storage and the grid. So we have one speaker from Korea. Then after that, we have a cross-cutting discussion with the 3 discussants. Among them, two are also the presenter, I think. Okay, so that's the way we are thinking how to organize this session. So first, I'd like to begin the first session focusing on the nuclear energy. First speaker is Professor Sang-Gun Lee of the Seoul National University of Science and Technology. He is an environmental economist working on the climate change, I heard. So the Professor Lee, floor is yours. Yeah, thank you.
Good morning, everyone. I'm Professor Sang-Jun Lee from Seoul National University of Science and Technology, aka Seoul Tech. It is different university with the Seoul National University. I'm from Seoul National University, but I'm currently working on the Seoul Tech. Okay, today I'm gonna talk about the direction of change of Korea's renewable energy policy. Let me introduce our problem in renewable energy system. We have only 8.9% of renewable energy for now, but we can ask why South Korea has a whole lot of problem about renewable deployment, such as public acceptance problem, and early 100 procurement problem, as he said. So we are focusing on the carbon-free energy right now, and we have power system shortage problem too. So only 8.9% of renewable energy, but we have a whole lot of renewable procurement problem for now. This is, I said, this comes from the renewable procurement, renewable deployment policy for now. So we are under the reform of renewable deployment policy for now. Okay, let me introduce electricity meet in South Korea in 2022. As this graph indicates, we have more than 60% of carbon, so fossil fuel generation for now. So it's much lagged behind in the OECD. We have as a carbon-free source, we have nuclear power a little bit low of 30%, and we have 4.5% of solar PV, a little bit of wind power. So we have just 8.9% of renewable energy in 2023, about 8% in 2022. Next one. Currently, so we have good sign. So in 2023, we have strong decline of carbon greenhouse gas in power sector in 2 years. the source is like this. We have demand increase, but fossil fuel generation has been decreased for 2 years in a row, and nuclear power generation has increased. So you can see nuclear power has played a large role decreasing greenhouse gas in power sector in 2022. Another source is solar PV. Solar PV deployment has played a role in greenhouse gas reduction in 2022. Next slide shows. So this slide shows the glimpse of how the renewable energy problem in Korea. So we have a little bit low renewable percentage, but let's look at the mix of between wind and solar. So in globally, wind power is little bit bigger portion than the solar PV. What about South Korea? We only have solar PV, so we don't have much of wind, and we don't have other source of renewables. This is the one problem of South Korea right now. Okay, let's investigate Korea's the condition for renewable deployment. So this summarize, I think professionals from Japan or professionals from Taiwan, you really think this one, you guys have similar problem in your country too. So in terms of geographical and technical problem, we have small land area, high population density. You know, high population density will militate against the renewable deployment because you have to gather public acceptance. In technical terms, South Korea has high PV technology, but in terms of wind technology, we are a little bit lagged behind the advanced countries like Denmark and Germany. And in terms of energy market, we have low retail price rate, so the renewable energy power is not so competitive in the retail market. And we have stagnated market reform, so retail, in terms of retail and wholesale market too. Today's, my focus is the RPS energy supply system. So renewable portfolio standard. So this interferes with the renewable supply and RE100. And so now we are expanding auction system. Finally, we have some good sign of corporate demand increase as Samsung Electronics or the SK Hynix, they demand a lot of renewable energies, but we have no strong financing and legal service and insurance to increase renewable energy portion. Now let's look at the problem of the Korea's RPS system. The Korea's RPS system, we have mandatory suppliers in terms of system, but the supplier's function is unclear. So on the RPS, so the RPS mandatory supplier has dual status. As a consumer, they have a strong incentive to minimize the cost, and they are suppliers too, so they have to maximize profit. So another one is cost compensation. So cost compensation by government. So the Korea, so your electricity bill. But so if you compensate your cost, you have incentives to minimize cost? No. And also mandatory suppliers stay focusing on avoiding fine or just management evaluation. So when they are under the management evaluation, they have strong incentive to meet fulfill the target. No economic way of fulfilling target. So they just instead they use the spot price, very high spot price that increase the renewable price right now. And so, as in sum, we have lag of cost to price decrease and no capacity building of renewable development. So still we have very big, so the high price in renewable energy. So this one summarizes these inefficiencies in Korea market. So RPS weight, oh sorry, we have some Korean. So RPS, so by the size of the solar PV, we have the bigger solar PV has lower cost. So 134 the Korean won by kilowatt hour. So in terms of economics, you have to increase the portion of bigger solar PV plant. But our current supply status is like this. 90% of solar PV plants are 3 megawatt under. Only 8% of the solar PV plant is 3 megawatt high over. So the RPS weight induce this kind of result. So cost price increase, and also we have many small power plants scattered all over the country that increase the power system burden. Next one. So by the RPS system, we have strong difficulty in managing portfolio and market size. We use the waste system, but we have no allocation by source. So we have problem of difficulties in predict or manage market size. That's why we have only solar, very short of wind and other sources. Next problem is the interference of RE100 procurement. So this graph shows the RE100 CDP's survey about the problem of RE100 procurement. So South Korea number 1, about 66 companies cited we have strong barrier to increase renewable in Korea. One big problem is RPS system, because RPS quantity cannot be procured by the corporate, because this is government mandate. So we have shortage of RE procurement. So next one, as you see, next number 2 is Japan, and number 5 is Taiwan. So 3 countries all have the RE100 barriers strong. So they face strong RE100 procurement the problem. Next slide. This one is as a reference case. This one price shows the RE procurement price in Korea. Now, average industrial tariff is about 161 by kilowatt hours, but RE procurement price is about just more than 201 by kilowatt hour by direct PPA, third-party PPA. Self-generate is a little bit low, and REC purchase is also more than 200. So, as a private company, you have to pay more than 50% of electric power rate to procure the renewable in the RE100. So this is a strong barrier. The price barrier of RE100 is exists in Korea. So that's why many Korean firms use only green premium. This just 10 won by kilowatt hour. Finally, this one summarizes our direction of change RE deployment policy for now. This policy is under discussion by the government starting from this May. So we have to pass the new renewable energy law in this Congress, but I hope we have to pass the law in this government. So the system is this way. So currently we are using mandated entity. They can procure renewable. So under the renewable energy portfolio, they have to buy. They can self-generate or spot market, or they can contract. They use government auction. In this system, no incentive to decrease the price. No, so this demand we is very highly competitive RE 100 demand. So this demand cannot be transferred to RE 100 demand by the companies. So we will remove this way. So government and renewable generator, so government provide the quantity and payment, and then RE generator through the government auction, they fulfill their contract, and so also they can choose they can sell to the private company. So we have more competitive market in terms of RE deployment, and we have more pre-market to supply to RE 100 demand. We have more like so orderly deployment in terms of RE deployment policy. So I hope this system will be introduced in near future in Korea. Okay, thank you very much. And this one, I think this experience is already exists in Taiwan and Japan. So we can discuss much more in the discussion section. Thank you very much.
Thank you very much, Professor Lee, for the case of Korea. Now we'd like to move to the case of the Taiwan, and Taiwan case will be presented by Professor Mao Shin Chang. He is the Dean of the College of Engineering at the National Taiwan University.
Okay, thank you, Mr. Chairman, for your introduction. Good morning, ladies and gentlemen. My name is Mao Shin Chang. I'm from National Taiwan University, and I'm also a professor at the Department of Engineering Science and Ocean Engineering. It's also the reason why I talk about the offshore wind in today's Trilateral Technology Dialogue. And also I'm director of an Energy Research Center in NTU. And I think I invited by TSED today, and actually I'm also a member of T-Stone. T-Stone is also actually a think tank of Taiwan government for the net zero. Yeah, so Taiwan government would like to provide $50 million per year to accelerate the development of emerging net zero technology. And our mission actually is to support the advice committee. The chair of the advice committee actually is the Minister of National Science and Technology, Taiwan. And I'm the group leader in the sustainable energy. And yeah, for today's talk, I would like to have a very quick view for you for today's situation in Taiwan for the offshore wind energy. And the first is the global situation, and then the wind energy policy in Taiwan, and the localization of offshore wind in Taiwan. And besides that, the industry development needs research and technical cultivation to support. So in Taiwan, we also have some research and technical cultivation for the offshore wind. Yeah, here you can see a very obvious trend. You can see, yeah, since 2021 is the exponential increase in the development of wind and offshore wind energy. In this figure, we can see the statistic from the Global Wind Organization. Yeah, and especially the outlook for the 2026, you can see here. Instead of Europe, East Asia will become the center of the development of the offshore wind. Yeah, it's also, but the figure you can see here actually is before the war between Russia and Ukraine. And after the war, yeah, here we also can see the main country for the offshore wind in Europe, like Netherlands, Germany, France, and the UK, Here you can see the original target development power of by 2030, and here you can see the new target. This country actually, after the war, the target become double of the original target. So that means that how about in Asia, in East Asia? In Taiwan, our goal is about 20 gigawatt by 2035. As I know, our data show in Korea, in South Korea, is about 12 gigawatt by 2030, and in Japan is 10 gigawatt by 2030. So we can predict after 2026, globally, the offshore wind, not only in East Asia, also in Europe and in the USA, where many offshore wind farms will start to develop. That means the supply chain, the maritime engineer will become a problem because it's insufficient at this moment. So in Taiwan, the energy situation, here you can see, before 2020, Taiwan only 2 energies in general. That means renewable energy is only 2%. And 98 must be import. And Taiwan government also has a goal to achieve the 2050 net zero emission policy. Here you can see, if we focus on the electricity, the renewable energy will have about 60 to 70%, and hydrogen is 9 to 12. Of course, the renewable energy with so high percentage, it must also combine with energy storage and smart grid together. And also, Taiwan government has a 12 key strategy. It's similar to Korea. And here you can see I will focus on the first one, the wind, because the technology is relatively mature at this moment. And the goal, in the short duration by 2025, you can see we will reduce the coal from about 50 to 27 and increase the renewable energy to about 16. And then the nuclear, because now we have 3 nuclear power plants over 30, 40 years, and it will be commissioned automatically. And and the total renewable energy by 2025 is about 30 gigawatt. Here you can see, and the main is the solar, and the solar 20 gigawatt, and the wind energy is about 6 gigawatt by 2035. And how about the wind? Because it's the reason why, in this figure you can see, why in Taiwan we would like to develop offshore wind. Here you can see the Taiwan Strait. Especially in winter, the monsoon comes from the northeast, from Siberia, via Korea, China, and Japan, and to Taiwan Strait. And here you can see in Taiwan center is a high mountain over 3,000 meters. And the other side in China also. So it's like the wind blow into a tunnel. So the wind speed will be increased automatically. So according to the Force Offshore, their report, there are top 10 the best wind farm, offshore wind farm. There are 9 sites in the Taiwan Strait, some in Taiwan side and some in the China side. This is the reason why in this figure you can see here the best wind field in the Taiwan Strait is here, but the blue line you can see is the 50-meter water depth because it's the technology boundary. Because the water depth within 50 meters, we can use bottom fix. That means like the onshore wind turbine, we can fix the wind turbine on the seabed. But in the region, we must use another technology I will introduce later, the floating type, because the water depth is too deep. So this is the reason why the Taiwan government would like to develop offshore wind since 2016. So the policy, we have 3 phases. Phase 1 is from to 2020, and phase 2 is from 2021 to 2025, and the phase 3 is 2026 to 2035. Here you can see in the phase 1 is offshore wind. We call DIP, Demonstration Incentive Program, because we don't have experience. So the government should support and 50% sponsor of the wind turbine for the project. And at this moment, we have 3 sites for the demonstration project. And here you can see in October 26 and in February 27, operation commissioned the first two wind turbines in Miaoli area. And here you can see after that we have 120 megawatt finished in October 2019. And here is a very short video for the record of the first wind farm. Because due to the time limit, I will skip some the video. This is in Taichung Harbor. Yeah, Taichung Harbor now become the most important separate harbor in Taiwan. Okay, now it is also become a cluster. So it's a new industry. Before that, we don't have a new learn. So the learning curve and the time actually is quite in this period is also very for not only for the industry but also for the government policy. We must learn how to change the policy and regulate the policy dynamically to push the industry develop successfully. Here you can see the second wind farm is in Taipei Power in Zhanghua. So in phase 2 we have 36 sites, but only 22 passed the environmental impact assessment. And finally you can see here 10 projects got through the selection. In the selection, the selection wind farm, they have the policy, they have the fit-in tariff and the commitment of localization. I will introduce the localization later. And another 4 wind farm is through the auction. So here you can see we have, till now we have a 2.3 gigawatt already finished and agreed. And yeah, here you can see a video, a short video about in the Ørsted offshore wind farm. It's till now the biggest single wind farm, 900 megawatt in East Asia, is already finished. So yeah, here you can see their localization for the local supply chain, and because they are Taiwan local supplier, actually need help from the European country and the European company. So the cooperation at this period is very, very important to help the Taiwan industry to solve the problem for the manufacturing and the design. Here you can see the pin pile. The welding already is also at the beginning. Is also a problem for the Taiwan industry, but now it has been solved. Yeah. Okay. In the next slide, you can see in the zone 3, from 2026 to 2035. Yeah, actually now we are today actually is the final review of the round, the phase 3 round 2 for the final decision of the 3 gigawatt. So yeah, the reason why you can see in Taiwan the policy is we did not open the wind farm together. Instead of that, we open the wind farm every 2 years, 3 gigawatts, and because the supply chain, the local supply chain need a continuous order, and so the policy now can help the local supply chain to develop further. And here you can see in the phase 3, the sensitivity area actually must be excluded for planning because like the fisher zone in North Taiwan, and also some ecological sensitive area also. And how about the localization? Because just as I mentioned, in the selection project, they have the commitment for the localization. Totally about 26 items must be made in Taiwan and or assembly in Taiwan. So for that, now in North, here you can see in North Taiwan, in Taipei Harbor, in Taichung Harbor, and also in Kaohsiung Harbor, we have the cluster already developed. In Taichung Harbor is the wind turbine industry, and in Taipei Harbor is the foundation industry, and in Kaohsiung Harbor is the maritime engineer. And also you can see here in maritime engineer is the most weak in Taiwan, because before that we don't have such kind of ship, the vessel. The vessel actually also a very huge investigation. So now at this moment we combine the local company with the European company together to the joint venture, through the joint venture to develop the vessel for the maritime engineer. And here you can see the different kind of the component and the tier 1 and tier 2 supply chain in Taiwan. And some result you can see the central steel now, it become the most important foundation supplier in Taiwan. And also, here you can see the other in South Taiwan, SDM, S for the foundation manufacturer. Here is the central power. And also the wind turbine. Actually, the wind turbine, of course, it come from Europe. Like Siemens Gamesa is a German company and manufacturer in Denmark. But the 40 megawatt will be, the assembly of nacelle will be as in Taichung Harbor. And since May this year, actually they are begin to assemble the 40 megawatt for the Taiwan wind farm. And also the 40 megawatt supply center over for the APEC country. And the blade you can see, the 9.5 Vestas wind turbine also has the manufacturing in Taiwan. And for the maritime engineering vessel, actually, especially for the foundation installation and the wind turbine installation, they need huge vessel. Here you can see the first vessel, we already finished the build and the operation in Taiwan wind farm, the so-called Green Jet. The Green Jet actually is can have 4,000 ton for the crane. It's the second biggest one globally now. And for the foundation installation. So I skipped the video, sorry, because okay. Let's have a short look about the research. For the industry development, research is also very important. Here you can see the first wind turbine in 28 destroyed by typhoon. It's an onshore wind turbine. So since that time, we cooperate with the Taiwan Power Company together to investigate the typhoon influence on the wind turbine. Here you can see in the Taichung region, the wind turbine. And after that, we have a national energy program. I am the PI of the offshore wind and the Marine Energy Center for the at that time, and till now. So here you can see the so-called TRL, technology release level. In renewable energy, in the TRL 4 actually is a small scale tank test, and the TRL 9 is commercial scale. So here you can see the next step is the floating. Okay. I have only 2 minutes. I will answer. And we survey globally the floating for the next for the deeper water. The technology is still not mature globally. There are more than 100 patents, but no one can persuade he's the best. So that means we still have an opportunity. So you can see the test project, the demo project globally. But now in Taiwan, we should have our own. So in a project sponsored by Ministry of Science and Technology Taiwan, we develop our own in Taiwan. We call it Taida Float. Taida is the nickname of National Taiwan University. So So we designed the platform, the floater platform, and the mooring and the anchor system in this project. Yeah, it's the wise. The length is over 80 meters. Yeah, so it's a quite huge platform. It's the mooring design and finally the system analysis. We can analyze the stability and the power generation together and the control together for the new design. Okay, and also we have a tank test. In the NTU, we have a model tank test. But it's the 1 to 100 scale model test. It's TRL4. It's only TRL4. So it's So the next step we would like to promote to the real sea test is TRL5 to 7. So it's need a quite huge budget. So in Taiwan government also have a demonstration project for the 14 offshore wind, and it will open this year, and selection maybe end this year or next year, and it must be finished by 2028. Okay, finally, I spent a minute for the education. For the industry in development, as I mentioned, they need talent. So since 2019, in NTU, we started the program, including the white collar. White collar is master course, including the engineer planning, analysis, management, finance, insurance, and the green collar. Green collar means they need a certification to operation, and like crane operation, jack operation, or the TP operation, they need the certification, and then they can do the work. And in NTU, we have the credit program already since 2018. And also we have offered the on-job training program. And in the future, we would like also the international for English program. Student got the 70 credit and they got the additional credit, and it can help them to join the industry. And for this training, talent cultivation, actually since 2018, we cooperate with Denmark Technical University together, and also we invited many the European industry to join the course, like Ørsted, CIP, the CEO, and the wind turbine manufacturer, Siemens Gamesa, and also the Netherlands government also offer a sea teacher training program for NTU. And also we have some international cooperation, like in Tokyo University, Professor Ishihara, and the Kyushu University, Uenomiya, and in Germany, it's the university I got a PhD from the RWTH Aachen. They also have a Center for Wind Drive, and Stuttgart University, and the Delft in Netherlands. Finally, it's the good time point to promote our triple side cooperation for the offshore wind. Here, because during the yesterday's talk, I summarized the figure. Here you can see in Europe, in wind turbine certification, foundation, maritime engineer development, they cooperate with each other. So that means not only one country to achieve all the engineer, but they cooperate with each other. How about in East Asia, in Korea, in Japan, and in Taiwan? At this moment, in Taiwan, we already have some, but for example, the wind turbine, the final assembly in the 40 megawatt in Taipei, in Taichung, but for example, the generator actually cannot be made in Taiwan because we don't have such kind of industry. So maybe it can be made in Japan or Korea, and then final assembly in Taipei. So I think it's we can compare in EU and in East Asia in the future. Thank you for your. In 2000, 23, KBS come to my lab to have a report about Taiwan offshore wind, the report. Yeah, so I'm here. So it's my lab. Yeah, it's my Thank you very much.
Okay, so thank you very much for the comprehensive introduction of the Taiwan experience of the wind power development and also the proposal of the trilateral technical cooperation. That might be the idea which can be discussed later. Okay, so I will move then to the Japanese case, and I myself will talk about the case. Okay, so I would like to talk about the case of Japan, especially focusing on the ratio of the photovoltaic and wind. As was mentioned by the Professor Lee at the beginning about the Korean case, the ratio of the photovoltaic solar is much higher than the wind. Actually, the same situation we can identify about that in Japan. This is the data based on the IRENA, the statistics, and you can see that you can see that the ratio of the solar is higher in Japan 2000, 2005, 2010, and 2015. Actually, the ratio increased around the 2015, 2020, 2023, a little bit lower than that, but still very high. In the case of the Korea, I'm not sure about the data of the 2005. Somehow, the ratio of the solar is relatively small, partly because of the commercial operation of the wind power I had around that time. But basically, the similar trend we can identify in 2010, 2015, and so on. So the question I would like to deal with is that why that happened. And basically, I try to identify the three stages, especially for the development of the renewable in the case of Japan. Initially, the research and development is promoted by government, and also the initial introduction diffusion strategy was taken at the end of the 90s. That was one of the push for the preference for the photovoltaic. Then after that, actually, early 2000, we have a system of the renewable portfolio standard that require specific percentage of the energy have to come from the renewable. In that period, actually, preference for the PV is relatively small, and actually the wind increased around that time. But again, after East Japan earthquake, there is a feed-in tariff system introduced in Japan, and that is a big push for the expansion of the photovoltaic, because from business perspective, that is the easy way to get profit, because there is relatively no small requirement for the consensus building and so on. Compared to that, in the case of wind, there is a heavy burden for the logistical work and negotiation and so on. That's the reason for the push for the solar again. But after that, as I will explain at the last part, there is an attempt for the rebalancing for the wind since around 2017 and 2018. And some, the effect can be observed, but still not effective. That's basically I'd like to discuss, focusing on the case of Japan. So in the case of East Asia, in the case of Korea and Japan, the ratio of the photovoltaic and solar is higher, but it's not the case of the China. In the case of mainland China, as this the graph shows, that the ratio of the wind is higher than the photovoltaic. Okay, so I'd like to go back to the origin of that. One of the initial push is the R&D effort by the government. Japan took the so-called Sunshine Project after the oil crisis, and as an attempt to develop the alternative to the oil, they tried to promote the solar energy and geothermal energy and coal gasification and hydrogen energy and so on. And after that, this was established in 1974, just before the oil crisis. But after the second oil crisis, the kind of the attempt was strengthened. And the so-called New Energy and Industrial Technology Development Organization, NEDO, was established in 1980. And there is a push for the solar to photovoltaic. So among the solar various technical options, originally solar thermal was the initial focus, but it was moved to the photovoltaic around this period. And after that, the New Sunshine Project was established in 1993. So around that time, this is just the graph of the subsidy. This is the subsidy to the PV, and this is the subsidy to the wind. As you can see, the vertical axis and the amount of the subsidy to PV is much higher than the subsidy to the wind around that time. That clearly shows the government preference for the PV for the R&D purpose at that time. And actually, the price of the PV relatively going down, but still much more higher than the current period in around the 1990s. And Japan tried to promote the diffusion of the PV, especially for the household. And actually, you can see the number of the solar PV at the initial period of the 1990s. So Japan is relatively the pioneer in that area, even faster than the case of the German. But German surpassed Japan soon after the turn of the century, actually. So one of the reasons why the government pushed the PV for diffusion is partly because of the regulatory policy. Japan introduced the deregulation of the electricity market in around the mid-1990s. And as a justification for that, the promotion of the PV for the household and buying the energy from the household to the electricity company is a kind of having kind of the symbolic meaning for justifying the deregulation policy. So because of that kind of mixing of the motivation, Japan put the subsidy for the PV. That's also the related reason why PV was one of the preferred target at the initial phase. As I mentioned, that initially Japan is producing more PV even compared to Germany, but German surpassed Japan around after the turn of the century. Then after that, as you can see, that the other country going faster compared to Japan. So the second period is the period from 2003. As I mentioned, that the renewable portfolio standard was established, and it forces the company to set specific percentage to be procured by the renewable energy. So because of the structure of the regulation, the company have to take an efficient option for the production of the renewable. And in this period, actually, the wind was preferred, even compared to the photovoltaic. So this is the data around that time, and blue is the amount of the newly installed wind, and red is the newly installed PV. And as you can see, that around this period, relatively small, but the wind grows faster than the PV. That's we can see. But in the third period, as I mentioned, the turning point is the East Japan earthquake. And because of the Fukushima accident, and there is a pressure for increase the renewable, the government at that time, Democratic Party of Japan, pushes for the renewable, and the feed-in tariff system was established in Japan. And especially at the initial period, the fixed price is set very high. So from the investors' perspective, newly investors' perspective, they have an incentive to invest in this area and get the return in a relatively short period. Maybe you can see that this is the graph of showing the approved capacity and the installed capacity. In the case of PV, as you can see, 2012, 13, and 14, there has been a rapid increase of the approval. So there was an application and the government approved that. But actual installation is only going up slowly. because it takes time and also, the industry investor would like to keep the right to be bought by the higher price. So they have an incentive to get approval, but sometimes they are slow to the real investment. Partly because of that, so there is a concern from the government that the PV goes up too high, too fast. Compared to that, wind also increased, but compared to the PV, the speed is much slower, and that is one of the concerns for the government. And one of the reasons why the wind power goes relatively slowly is that there is a requirement for the environmental assessment and getting negotiation and so on. Those are the kind of the factors which prohibit the quick introduction of the wind power. So this is the case of the wind power. Concerning the absolute amount, it's much smaller than PV, but pattern is similar. The getting approval relatively earlier, but actual implementation is very slow. And even compared to the PV, actual implementation is slower in the case of wind until around the 2016. Okay, so this is the same graph, having a time horizon longer until recently. As you can see, in the case of the photovoltaic, the approval amount is basically fixed, but the actual installation going up incrementally. In the case of the wind, actually the approval amount increased to some extent, partly because of the change of the policy, as I will mention later, but actual implementation is not so increasing rapidly. That we can see from this graph. Okay, so having those kind of a picture in mind, the government tried to change the policy. The first point is that they do not push so much the emphasis on renewable initially, but around 2018, and then in the government energy strategic plan, renewable energy was identified as a primary source of power. In that respect, the role of the renewable increased substantially. But as I mentioned, that there is a kind of the unbalance between the photovoltaic and the wind power. So one thing government did was that revising the feed-in tariff so that sudden increase of the PV will be controlled. That's one thing. And also partly because of the concern about the slow increase of the wind, the government tried to rebalance the ratio between the photovoltaic and the wind power, and they tried to facilitate the new system to strengthen the installation of the wind power. So concretely, the act promoting the use of the sea area for the development of offshore power wind was established in 2018, and it was implemented since 2019. Actually, this is initiated by the Japan Business Federation, the Keidanren. And one point is that there is an issue of the coordination with the fishing right. The partly because of the historical use of the ocean by the fishing industry, the use of the maritime surface is limited by the very weak institutional infrastructure. It means that only 2 or 3 years operation is permitted, but longer term commitment is necessary for the offshore wind power. So the kind of coordination mechanism with the fisherman is established. That's one thing. And another thing is coordination with the grid issue. So if the wind power produce the energy, it have to be transmitted to the consuming area. So the grid connection is very important, but it also have a problem. So those two issues are expected to be solved by this new law. But actually, when implemented this law, there has been some the problem, because this law established a very detailed process for the getting agreement among the stakeholder. And this is very the detail in that sense. It's good, but basically the process should be coming from identification as a potential area. Then after that, there has been a consultation process. After consultation process, if consensus is made, it will be designated as a promotional area. But the problem is that for getting a status of the potential area, it is expected that there is a kind of an agreement among the major stakeholders, including fishermen. But who will take the responsibility for taking the initial, the negotiation, a kind of a pre-formal process? So that is actually the issue, and the process do not move so fast. So this slide explains about the issue I mentioned. So okay, so that's the development so far. Basically, as I mentioned, that there has been a preference for the photovoltaic, basically, in the case of Japan. And the reason for that is one of the technical preference, and partly because of the combination with the regulatory policy, and especially after the East Japan earthquake, because of the rapid investment from the independent power producer, try to get the benefit from the short-term investment. So compared to that, there is recently a sign of the getting more wind power operation. And for that purpose, the legal system was changed. But so far, the actual progress is very low. So that's the current situation. But finally, the reason for the delay of the wind is that partly because of the grid connection, but partly because of the commitment of the government, and especially the consensus building issue, especially before the potential designation as a potential area. That's one of the big reasons for the slow. Putting in the broader perspective, after around 2020, Japan also committed to the carbon neutrality, and a series of the strategy policy was taken, including the green growth strategy or the green energy strategy, and the big fund was established to facilitate that under the framework of the Green Transformation Promotion Act. In that, those are the kind of area which is identified for the R&D development, and offshore wind and solar heat energy. That's one of the major area. And actually, this is the expected amount to be invested in this area, and the renewable is actually one of the major focus. So from the finance perspective, there is a kind of the mechanism for support, but whether it's enough for actual implementation or not, that's the issue to be contemplated. Okay, so that's the development in Japan and the current issue. So thank you very much for your attention. Okay, so far those are the three cases about the renewable development in the Korea, Taiwan, and Japan. Now we'd like to move to the next group of the presentation about the nuclear case. So first, I'd like to ask Professor Yong-Po Lee, the professor of the nuclear engineering at the Seoul National University. The floor is yours, please.
Good morning. My name is Yoo-Ho Lee, and I'm an associate professor at the Department of Nuclear Engineering. And today I was asked to give a talk about the small modular reactors and its relation to the increasing demand in the field of the AI. So I prepared a few slides talking about some details. So just giving you some backgrounds of my profile. I'm basically half nuclear engineer and half material scientist. I'm working on the nuclear fuel materials and the reactor safety as my research fields. And before joining Seoul National University, I was a professor at the Department of Nuclear Engineering in the University of New Mexico in the US. So with this information, I would like to start the presentation about the SMRs. So SMRs, let me give you a very brief definition of what SMR means. So SMR consists of the two keywords, which is S and the M. So the S represents basically the small, but how small is small? typically the large nuclear power plants are built with the size of about 1,000 megawatt electric. But small modular reactor specifically represents or means the reactors whose power output is less than 300 megawatt electric. So it is basically 1/3 of the typical nuclear power plants we build in the large scale. And the next keyword we have is the modular. So probably we are all familiar with what we mean by the modular. Modular means we want to actually fabricate the nuclear components and the construction parts as much as we can in the factory, and we want to actually assemble that in the factory, in the site. So by doing so, we want to maximize the factory work and minimize basically the construction work. So, and on top of that, the small modular reactor looks quite different from the typical large scale nuclear power plants. As you can see in the left figure, large nuclear power plants has like this distinctively large components connected in the pipes. But small modular reactors, we plan on building everything in an integral manner. So in this big shell, everything is in there, like steam generator, reactor core, and all the other necessary components are integrated in this big shell, such that the design is much more simplified. So let me make some simple comparison of the size. So if we want to make an apple-to-apple comparison between the small nuclear reactors and the large nuclear power plants, if this one is the large nuclear power plants drawn in scale, comparatively the small nuclear power plants are much smaller, as you can see. So it's a quite revolutionary technology, I would like to say. But why is revolutionary change in the nuclear power plant construction important? That's basically, that holds key to understanding the very motivation behind the small modular reactors. So I'm actually showing you some research results published in the journal Energy Policy. So this graph shows basically the date of the construction start, and the y-axis shows basically the construction cost of the nuclear power plants for various countries. But as you can see, one very interesting result is the US data. The construction cost of the US skyrocketed from like late 1970s. And that's partly because of the TMI accident, which destroyed the supply chains, and also the enforcement of the very conservative regulations resulted by those accidents. So as a consequence, US lost basically the economic competitiveness in the nuclear power plants. But the only country that experienced the sustained construction cost reductions over the period of the time is Korea, which is shown in the purple. But nevertheless, what you can see in common here is that large nuclear power plants do not really exhibit very strong record of learning curve in terms of the cost reduction. But Korea has been doing excellent compared to other countries, as you can see. But nevertheless, it's different from the iPhone. If you build the iPhone, you build more, of course, the cost of the iPhone goes down. But the nuclear power plant, because we are so much dependent on the construction work, this learning curve is not so clear. So that's basically the challenge faced by the Western world, and driven by the Western world's interest to redefine the way of building the nuclear power plants, the small modular reactor emerged. So that's what it is. And also on top of that, the recent failures witnessed in the Vogtle nuclear power plants. The Vogtle nuclear power plants, Unit 3 and 4, are the recent US nuclear power plant campaigns built in Georgia. And as you can see here, it took 7 more years than planned, and it experienced a significant cost overrun, which actually is about 17 billion. So these Vogtle plants we saw in Georgia really represents the current the status of the large nuclear power plant construction and the economic competitiveness of the US. So that's where we are standing at the moment. So the SMR wants to redefine the way of attaining economic competitiveness. So let's look at the typical way of attaining the economic competitiveness of large nuclear power plants. If you think about it, in Korea, we teach students that nuclear power plants are always cheaper than the renewable, especially in Korea. But if you really think about the reason, it is quite surprising. Why? Because the nuclear power plants, you need extra components, extra safety features, you have more regulations, and people are more expensive. But how could electricity still be cheaper than most of the energy sources? And that's one of the reasons is that we build everything in large scale. So we actually leverage or capitalize on the economy of the scale. And that's possible because in nuclear power plants, we can increase the power density of the reactor using very detailed or very sophisticated reactor engineering. So the grammar of attaining economic competitiveness for large nuclear power plants has been largely based on building everything in a large scale. But as a result of that, we've been relying so much on the construction processes, and we need to actually improve our cost competitiveness. So for the SMRs, instead of relying on the classical or traditional grammar of building everything in large scale, we want to actually go after a new avenue or new path of achieving the economic competitiveness. And that's modularization, and that's design simplification, and design standardization, and regulatory harmonization. So by leveraging these four aspects, which we didn't really experience in the large nuclear power plants, we want to attain the economic competitiveness of the small nuclear power plants in a different way. So that's basically one of the very important effects. And let me make an analogy with the apartments. So probably you are, most Asian, the big cities in Asia, like China, Korea, and Japan, the house prices are very expensive. And if you think about purchasing a house, you always think about the areas. And I'm showing you the typical two houses of Seoul. One has like this big area, 238 meters square, but the price is 1.8 million USD. Let's look at the other house option, which is about 580K USD, but the area is much smaller. But let me ask you a question, which one is cheaper? If you think about the absolute money, of course, the smaller one is cheaper, but if you actually divide the price by the area, of course, the larger is the cheaper. So what we all know is that the larger larger apartment, like nuclear power plant, is cheaper per area, such that it is always an attractive option to go after if you have unlimited resources. But in reality, where resources are limited and the type of family is diverse, the smaller apartments can be demanded as long as it is supplied at a reasonably expensive cost per area, right? So that's basically the mechanism behind developing the small modular reactors. I don't think it can be cheaper than the large nuclear power plants per energy production. However, if this cost can be managed at a reasonably cheaper level, this can be very much demanded as we demand the small apartments in Seoul. So that's probably holding the key to understanding the economics of the small modular reactors. And also on top of that, the construction time of the small modular reactor is much shorter than the large nuclear power plants. These days, things are happening in a very fast way. You don't want to invest your large chunk of money thinking that you can get some return after 20 years or so. People want to invest, and the people want to actually get the return as quickly as possible. So by reducing the construction time, by maximizing the factory work, we can promote or we can foster the investments of the private sectors. As a consequence of that, there are many private companies trying to develop the small modular reactors these days internationally. And on top of that, SMR does not require as big siting as as large nuclear power plants. So that's basically because we don't need that many emergency planning zones. This is important because every nuclear power plant has what's called the emergency planning zone. That needs to be specially managed, right? But because SMR is much safer than large nuclear power plants, we don't need that large emergency planning zone. And this actually means a lot, because by requiring smaller emergency planning zone, SMR can replace retiring fossil fuel power plants, because we have fossil fuel power plants which are that are meant to retire in the next several years, not only in Korea but globally. But large nuclear power plants cannot replace these retiring fossil fuel plants, because large nuclear power plants needs a lot of the areas that needs to be specially managed in case accident happens. But small modular reactors, we don't need that much space, so that it can readily replace retiring fossil fuel plants. And this is very helpful, because as we said, the small modular reactors is not leveraging the economy of the scale, but by leveraging or by using the existing grid lines and existing infrastructures of the fossil fuel plants, we can gain economic, or we can enhance the economic competitiveness to certain extents and compensate for the economy of the scale. And on top of that, SMRs allow load following and provide a total energy solution. So SMRs are designed to operate beyond the base load. You know, typically nuclear reactors operate 24/7, but small modular reactors, we can do the load following, but not only we provide electricity, but we can provide heat for various energy applications like hydrogen productions. But what I want to say is that nuclear is a greenhouse-free energy source. This is basically the amount of the carbon dioxide emission per energy production. And nuclear is almost as low as the wind. So it is basically the clean energy. But better yet, nuclear is the only scalable clean energy that we have in our energy portfolios. So this makes actually nuclear very enticing energy source. And on top of that, nuclear's safety is not arguable, because I'm showing you the death rates per unit of the electricity production, and this is basically the how much expected death you need to be prepared for the energy production with the various sources. And the nuclear is much lower compared to these conventional energy sources. And we have like almost the lowest death per energy production. So nuclear is safe. So that's something not arguable, but it's basically the matter of the public acceptance and our perceptions. So that's where we stand. So there is a large number of the international SMR developments happening in the world, as you can see here, driven by many of the US, Europe, and the Asian countries, as you can see here. So Korea already developed a decent small modular reactor called SMART long time ago. These days, SMRs has become almost a buzzword, but before SMR became very popular, SMART was already developed by Kerry, and it already passed or attained the standard design application. And Korea actually is one of the leading countries in doing this. But one of the commercialization strategies of the SMART was that because we want to do this everything very fast, for license suitability, the innovative technologies are relatively excluded in the development of the SMART, but the cost is a little bit expensive, so that today Kerry is doing the new work to actually redefine or re-increase the economic competitiveness of the SMART. And on top of that, today ISMR, which is the new reactor type, small modular reactor type of Korea, is being developed. And also we are shooting for the SDA, the license application, in 2026, and we expect to acquire the license in 2028. By doing so, I expect that Korea can quite dominate the SMR markets in the future if everything goes successful. So let me just connect what I explained in the nuclear power plants with the AI. So this is a quite interesting chart showing how much energy is required per request. So if you do the Google search, per search, you need about 0.2 watt hour of the energy. And this is increasingly increasing. For ChatGPT, it costs much more energy because it is basically engined by AI and some of the machine learning techniques. And we are expecting to have maybe AI-powered Google search in the future, and it will require much more energy than what we are using today. So using this information, people try to, the International Energy Agency expected the electricity demand from the data center, AI, and cryptocurrency. And today, when the data was fabricated, it accounts about 2%. But in the next several years, in 2026, you can see that this energy demand is increasing quite fast. And how much we need by the end of the 2026, if we follow some conservative assumption or marked by the green line, this accounts for the entire country of the Sweden. And if we go for the red line, that accounts for the entire country of like Germany. So this energy demand by the AI center and the big data is real, and we need to actually prepare for it. And in case of the US, and actually this is primarily driven by the US and Europe. And in the US, the current data center electricity portion is about less than 5%, but by the end of the 2026, it is expected to grow up to almost 6%. And this is very interesting because in case island, 30% of the island's energy consumption will probably come from the data centers in the future. So this is actually happening in Korea. So recently in May, there's an 11th basic plan for long-term electricity supply and demand of the Korea was released. This actually is basically the national program that outlines the expected energy consumptions of Korea. And we need to actually plan for it. So we have about 26 nuclear power plants operating today. And 4 are already planned or being constructed. But this committee evaluated forecasted demand. It actually expected 129 gigawatt needed by the end of the 2038, but we always need to have extra reserve margin of 22%. If you multiply this, and then we have already many things being built or planned, including the renewables. And if you subtract this value, it requires that extra 10 gigawatt is needed. And what you can see here is that of which 16.7 gigawatt is newly assessed demand. And among this 16.7 gigawatt, 4.4 gigawatt comes from the AI data center. This is not a small number because that accounts for almost 4 units of the large nuclear power plants. So that's where we are standing. And the current government's direction is that among these 10.6 gigawatt needed, extra 10 gigawatt, of which 4.4 gigawatt will be supplied from the nuclear. So that's where we are standing, and the nuclear is carbon-free, so we can probably do this with a carbon-free energy source. But there are also challenges because there are many new SMR projects being planned internationally, but not every new SMR is realized because of the difficulties associated with the engineering and licensing. So it is always important to come up with the realistic and the feasible SMR concepts. But even if it gets the license and everything is ready, actual deployment of the new SMRs needs to overcome the economic barriers. So the thing is that you always need to, it is very important for us to achieve economic feasibilities. So in the world, there are not many SMRs being deployed today, but this SMR that we are building, we are developing in Korea, ISMR and the Advanced Smart, will probably be better shape compared to all the other SMRs in the world. So there are 3 things that are happening in Korea which actually give new opportunities for the Korean SMR industries. So we have extensive success in large-scale nuclear power plants, licensing, construction, and operation, and export. And this is almost unmatched level of success compared to any other country in the world. And on top of that, Western world is suffering from losing the economic competitiveness of the nuclear power plants, which also gives us many opportunities. And as shown by our success in the export to UAE, we are actually looking for the export of other European countries to be seen in the future. And on top of that, the nuclear is gaining more attention than ever because it is basically the carbon-free energy source and only scalable one. So today, the Korean nuclear represents the most viable and economically competitive technologies in the Western world. So with this, I think the future of the nuclear and the SMR is bright in Korea. Okay. So with that, thank you for your attention.
Yeah, Professor Lee, thank you very much for your introduction of the SLR in general and also the potential and limitation. Okay, now I'd like to turn to the Taiwan case. Professor Wen-Lin Tu, she was the moderator yesterday, so you already know. She's the director of the Research Institute for Democracy, Society, and Emerging Technology, and also the dean of the International College of the Innovation at the Chengdu University.
Thank you, Professor Shirayama. And again, on behalf of DSET, I'm very, I want to express my gratitude to the Institute for Future Strategies. And thank you for inviting us here, as well as our partner, including T-Storm and Taiwan AIA. And I should say that I'm not the nuclear technical person, so I'm very appreciate Professor Lee, just like showing, how's the SMR. But I want to share the prospect and challenges of SMR in Taiwan. I think that's give a very different story from our Korean partner, and. So in the past 5 years, I also, get involved in working with governmental sector on the social communication over the nuclear waste siting issues. So today's my presentation will talk about Taiwan nuclear policy toward its net zero goal, and also our major technical and social concern about the conventional nuclear power plant, as just Professor Lee mentioned about the large nuclear power plant in Taiwan, and also the promise and challenges of SMR, and the opportunity for the cooperation between Taiwan, Japan, and Korea on this matter. So I think this slide Professor Zhang just showed, in his presentation. So, based on the National Development Council forecast, the composition of the electricity mix by, I want to direct you to see in 2050, it should be, renewable energy account for like 60 to 30%. And the hydrogen, the 12%, and gas and CCUS is around like 20 to 27% to meet the electricity demand and the Taiwan net zero goal with the emission and absorption. So in this picture, the conventional nuclear power plant is not really, like in the future power scenario of 2050. So the slide shows that in 2023, which is last year, the share of renewable energy already surpassed the nuclear energy. So under such a scenario, we expect a gradual decrease in Taiwan's dependency on hydrocarbon and conventional nuclear power. And Taiwan launched its first decommissioning project of its first nuclear power plant in 2019. So I'd like to give you a little bit background about the nuclear infrastructure and the waste problem in Taiwan. So in this slide, you can see there's a kind of long time protest against the construction of the fourth nuclear power plants, which designed to advance the boiling water reactor unit rated at 1,350 megawatts each from the late 1980s. The social upheaval suggests the widespreading insecurity about nuclear safety after some serious nuclear accident worldwide, like Chernobyl or Fukushima. And it's being sealed up, and the fuel road has been shipped out. And this also suggests Taiwan's determination to phase out the nuclear power plants. And since Taiwan does not have a nuclear industry to cover the fuel cycle like Japan and Korea, and all material and services are imported. And one of the top issues in the downstream radioactive waste management, the Taiwan has had a hard time to find a final disposal site for nuclear waste. So the site selection of nuclear waste is very challenging and unsettled until this very moment. And this historical context of Taiwan's conventional nuclear power plants development suggests how social communication and radioactive waste management are the pressing issue for developing the advanced nuclear power plants in the future. On the other hand, it also suggests how the social and technical cost of running nuclear power plants in Taiwan really differ from those in Korea and Japan. So according to our enforcement rules for the implementation of Nuclear Reactor Facility Regulation Act, the decommissioning of nuclear power plants should be completed within 25 years upon obtaining the permit for decommissioning granted by the competent authority. And accordingly, Taiwan's decommission of its first conventional nuclear power plant is here. Okay, on the top. It started in 2019. By 2025, there will be no conventional nuclear power plants interconnecting to Taiwan's power grid. So you see the third nuclear power plant is on the south tip of Taiwan. And it will be decommissioned very soon in 2025, which is next year. And so Taiwan's this slide shows Taiwan's long-range power development plan of 2023. So based on our national utility and Thai Power Company development plan, it's clear that Taiwan's power grid would integrate with more combined cycle gas turbine plants, that is the gas-fired power units in the coming years as a base load energy. So all the green is the combined cycle gas turbine. But renewable energy growing share of the total electricity generation should be also reached to 27 to 30% by 2030. So in this scenario, you can also see the conventional nuclear power plant plays no role in this picture, but the advanced nuclear power plant came into discussion regarding the possibility of offering stable and clean electricity that matches Taiwan's net zero goal. A possible contribution by substituting a certain amount of power generation from gas is probably a promising role the ANPP might play in the net zero future. So talking about the filling the gap, SMR may have other promise in terms of its very different characteristic Professor Lee just mentioned. So the first one is equipping a passive safety system. As you know, that Professor Lee just mentioned, it's like comparatively safe to the large nuclear power plants. And also, I think second, the low carbon electricity for industrial power needs. he also mentioned about a lot of AI chips and a lot of semiconductor manufacturing needs a lot of power. So it will offer, like the manufacturing and testing could be carried out directly in the factory, guaranteeing the best construction quality and shorten on-site assembly time and easier decommissioning. So this is all the benefit of the SMR. And it also can provide the wide range of industrial application in heating process, not only for the electricity generation. So the extending current nuclear research into SMR, for example, the safety enhancement of light water reactor, the safety analysis of the reactor containment and the heat removal in the spent fuel, also means furthering Taiwan's development in the advanced nuclear power plant in general as well. However, I think developing SMR has a lot of challenges under Taiwan's current nuclear policy, like lack of nuclear industry and also other limits. So the relevant research remains in the very preliminary phase. And in Taiwan, installing SMR at the industrial complex or within the factories would still face the problem of limited land mass. This is perhaps why there have been only Formosa heavy industry or TSMC with higher manufacturing capacity showing interest in developing SMR. And the nuclear waste generated from the SMRs would be higher than the conventional ones. So when the final disposal site remained unknown in Taiwan, SMR's installation would impose even higher pressure on the already protracted negotiations. So in general, I would say Taiwan has not yet drafted its long-range planning for introducing advanced nuclear power plant, and especially in terms of licensing and the corresponding modification of regulations. For instance, we only have safety and operational regulations for light water reactors. So we might need to adjust them to accommodate the same type of SMR. In addition, the Formosa heavy industry and the TSMC become the first user of SMR. Then Taiwan Electricity Act will have to undergo another market regulation to allow these companies to run their SMR in their campus as the independent power producers. So all these challenges made the commercial operation of SMR very unlikely to be added to Taiwan power system before 2050. Instead, we may value the scientific merits of SMR research that might prepare Taiwan for the future AMPP in general, which could be possible based on essential collaboration with Japan and South Korea. So there's an opportunity for cooperation based on some kind of shared challenges like energy, climate, geopolitical among three countries. For example, that we have a higher energy import and the surging demand for clean electricity. And also Taiwan and Japan have all the concern about the earthquake and also the potential geopolitical threats like South Korea, North Korea, and Taiwan and China. And also we all face a sea level rising and the climate change challenge. So there's a possible science and technology collaboration. From 2009 to 2018, Taiwan launched 23 projects in advanced nuclear research. And we can categorize the three significant areas from the brief word cloud generated from the project keywords. That's including cold physics, thermal hydraulic safety, and structural material. And and also, I think the molten salt reactor that could utilize the high-level spent fuel would be ideal in Taiwan's case. To deal with the nuclear waste, so that also attract the research attention. And to pick up the path of scientific and technology advancement from 2018, further collaboration in advanced nuclear research among Japan, South Korea, and Taiwan can be expected. And here that you can also see like some partners in Taiwan, and I think the professor probably know like many of the institute, and you can see the counterpart in Taiwan about the atomic, the Energy Institute, Research Institute here. So that comes to my conclusion. I think this presentation that offer the uncertainty of SMR in Taiwan, the present situation, including the corresponding regulation change, talent nurturing, a limited landmass in terms of site selection, radioactive waste management, and the cost-benefit analysis in Taiwan would very different from Japan and Korea. And the current assessment of the feasibility of SMR or other AMPPs such as Taiwan rather important strategy in focusing on the renewable energy development to reach the net zero goal. So renewable energy technology are categorized by their decentralized nature and the possible enhancement in balancing regional load and its empowerment to the civil society, which has been highlighted in Taiwan net zero policy. Instead of filling the gap or replacing the current development of strategic energy technologies, the opportunities and the uncertainties of applying SMR in Taiwan suggest a transition stage. In other words, taking the international science and technology collaboration of SMR as an opportunity to help Taiwan be prepared for the broad application of AMPP after 2050. But we also like to address that the facilitating a new set of policy regulations for AMPP, Taiwan must consider this energy policy with land planning, social consensus, and industrial development to ensure a smoother transition from the conventional to advanced nuclear power plants, if that's the path we want to pursue. So that's the end of my presentation, and thank you very much.
Thank you very much for detailed explanation about the SMR in Taiwan and also the broader issue relating to the ANPP, including the social and contextual issue. Okay, now we'd like to move to the nuclear issue from Japan. We have Professor Oda, the professor of the nuclear engineering of the Seoul National University.
Thank you, Chairman. My name is Takuji Oda. I'm a professor of the Department of Nuclear Engineering, Seoul National University. So today I'd like to introduce an overview of Japan's nuclear energy policy, key challenges and opportunities. So basically my talk has 4 contents. The first, the long-term comprehensive energy policy in Japan, very short, so as already Professor Shiroyama talked. And then my second part is about nuclear energy policy in Japan especially for the last 10 years after Fukushima. And then the latest, the 6th strategic energy plan I focused on. And then I would like to summarize my talk with challenges and opportunities. And also I would like to make my short introduction. So my research field is, as I said, with Professor Yuho, basically nuclear materials. So the closest colleague in my department about research field is actually Professor Yuho. So both of us are from nuclear materials. And also as I said with Professor Yuho, I work for science and engineering of materials. And some differences also I work for nuclear fusion, not only fission. And the education background, I basically got all education in Japan. And then after 1 year, a kind of postdoc period in the USA, I moved to SNU in 2013. Okay, so let me start my talk. The first part, the long-term comprehensive energy policy in Japan. So basically in Japan, the direction of comprehensive energy policy has been set by the long-term energy demand and supply outlook. So from like 1950 or 60, very early, around 70s. And then in 2002, the strategic energy plan was enacted to promote long-term and comprehensive energy measures for energy supply and demand and realize 3E, so energy security and energy efficiency and environment. And basically this plan is revised every 3 to 4 years. So starting from the first plan under Prime Minister Koizumi in 2003, and the latest one is 2021 under Prime Minister Suga, and then probably this year we publish a revised version for this, the strategic energy plan. So about the nuclear policy, also the most important policy, I believe, is the strategic energy plan. And it is mentioned about nuclear in the first plan, so promote nuclear power generation as a key power source. So it was mentioned. And then in the third plan, under Prime Minister Hatoyama, so numerically targets were very clearly set. To increase the ratio of zero-emission power sources to 34% in fiscal year 2007 to more than 50% by 2020, and probably around 70% by 2030. So this zero-emission power sources include nuclear and renewable energy sources. So it was a very ambitious, plan they set. And this includes some plan to construct at least 14 new nuclear power plants by 2030 from 2010, and an increase in the capacity factor, so how much we run nuclear every year. So it's like we try to target like 90% from 60% in 2008. So why they set this kind of very, the ambitious plan is because they want to meet the greenhouse gas emission reduction target by 25% as of 2020 from 1990 levels. So they got very, ambitious plan. But as you know, we have the Fukushima accident, and then plan was very changed. So Prime Minister Hatoyama and Prime Minister Kan came from the same party, but they very changed the plan after Fukushima accident. So in July 2011, so Prime Minister Kan stated that the future energy policy should aim for no nuclear power, and that the third strategic energy plan would be withdrawn. And then the government formulated the innovative strategy and energy and environment on September 2012. But still, government understands no nuclear is very difficult at the moment of 2030. So then in 2030, their target after nuclear Fukushima accident was 15% nuclear. But anyhow, 3 major goals were set by this policy: that society not depending on nuclear energy, to enable no nuclear by 2030s, and then also green energy revolution and stable energy supply. And then this first one about nuclear part, also we have 3 principles. Strictly apply 40-year operation regulations. So no extension, but they finally actually accept one-time extension at that time. And then only those nuclear power plants whose safety has been confirmed by the Nuclear Regulation Authority will be restarted, and no new additional nuclear power plants will be built. So it was set in 2012 as national policy. And after that, Prime Minister Abe came, and his time was very long. And the fourth one, the energy policy, 2014, so reduce dependency on nuclear power as much as possible. So this statement was kept. So this one was basically came from the previous, the third version. But policy of zero operation of nuclear power plants in the 2030s by the previous government was withdrawn because it would be impossible. So relatively, they changed to more, nuclear policy supporting. And also they removed no new construction policy, but they didn't mention new construction, but they just removed the policy, the no new construction. And also they mentioned nuclear power is an important baseload power source in 2014 policy. And based on this, the strategic energy plan, the long-term energy demand and supply outlook 2015 said the energy power mix level of nuclear to 20 to 22% in 2030. So they say they want to reduce the dependency, but anyhow, they actually quite depend in the real plan. So maybe this is a political reason. So they cannot, remove this statement, the reduced dependence, because they remove this one, maybe anti-nuclear people maybe respond very strongly. So they want to avoid such. And then keeping this statement, but target is still, it's clear. Nuclear is one of the baseload, important energy source. And then fifth one, again, Prime Minister Abe, approved by the cabinet 2018, basically the same. But still, the dependence on nuclear power plants should be reduced as much as possible. This statement is actually kept even the latest one, the sixth version. And then anyhow, after Fukushima accident, so what's happened is nuclear, yellow one, it's about the power generation. So yellow one becomes 0 once, and then after that we restarted about 10 reactors already. And at the same time, green one, renewable energy, as Professor Shiroyama introduced, the solar PV very increased. Now our level of solar PV is very close to almost same with Germany level. So we very, promoted the solar PV. And then this is the latest one, 2011, by Prime Minister Suga. So there are two major targets. So carbon neutrality by 2050, this is a very big target. And also 46% reduction in greenhouse gas emission in 2030, and possibly also target like 50% as ambitious target. But to achieve them, so both renewable and nuclear needed to increase significantly. So this one is as of 2019, the energy mix. So renewable 18%, nuclear 6%. So this should be increased to 22% nuclear, and renewable to like about 36, 37%, 8%. And this one is very challenging because solar PV Japan very introduced already, as Professor Shiroyama introduced. Maybe we need some wind for renewable part. And also nuclear part, we have to restart many, many reactors indeed to achieve this target by 2030. So we have just 6 years to go. We have to increase a lot. And what is this 22% means? So it means basically in total we need 186 billion kilowatt hour out of this all the electricity needed in Japan 2030. So it corresponds to about 26.5 gigawatt capacity 2030, about 80% capacity factor assumed. And this 26.5, roughly speaking, is like 26 big reactors. It may be not so difficult, but it's actually not so easy. So Japan actually had like 45, 50 before Fukushima accident. So you think it's easy to reach 26.5, this pink one. But now, Japan, once we had 0 nuclear, and then we are at here about 10. So we have to come to here, to keep increasing, restarting nuclear reactors without maybe any delay. And also, basically government want to keep this level probably very same in 2050 and later. So it means we have to keep this level. But to realize that, what we should do first, we have to restart almost all reactors by 2030. And then after that, at 2050, many reactors maybe go to retirement. So we have to make new reactors. So in Japan, we need construction of advanced reactors. So government think this one is very important. So now government very push development and construction of advanced reactors, realize this one around 2040, 50 to replace this kind of retirement of all the power plants, light water reactors. And then, so this, to achieve this, the restarting almost all power plants, this one is not easy. Why we can think so is because so far, Japan restarted about 12 reactors. And this one shows where we have reactors. And this circle indicates PWR, pressurized water reactor. It's a different type of Fukushima reactor that suffered accident. And this square one is BWR, the boiling water reactor. It's the same basically sort with Fukushima. So far, what Japan restarted is basically PWRs, especially the West Japan, not East Japan. So 12 one already restarted, and from now on, what are remaining one is 4 PWRs. Maybe this one not so difficult. And then, but after that, we have to go to BWRs, the same sort with the Fukushima power plant. And then, even BWRs, not TEPCO's one, maybe it's okay. So TEPCO is the utility company that owned Fukushima damaged reactor. So we have 15 plus 3 new reactors. So for example, Onagawa 2, it's the Tohoku, so they plan to restart this year, September. So if this one successful, maybe it's nice for us. Maybe we can expect we can restart these of them. And after that, we have BWR of TEPCO. Maybe this one is more difficult. We have another challenge. So we have to, finish these challenges. It's very not so easy. But good point is public opinion is a bit changing, a bit more favorable compared to just after Fukushima. So this is a kind of public opinion poll by newspaper companies, different sorts, from left to right, different policies. But all of them show very similar trend. So agree of restarting, so initially it was like 30-40%, but now it's increased about 50%. And disagree of restarting also is decreasing. So probably the situation is improved, but we have several challenging BWR and TEPCO's BWR and so on. And then, of course, as I already mentioned, so Japan also want to replace some retiring light water reactors with new reactors. So maybe SMRs, as Professor Yuho introduced, it may be very attractive option, but as far as I check Japanese policy, at least the government level, the most important one would be fast reactors and high temperature gas reactors. So why I say so is this is about the budget. So this is 2.5 billion Japanese yen is fiscal year 2004 budget, and then SMR is just 1 billion Japanese yen as government support, direct support. But fast reactors, they put a lot of money, and high temperature gas reactor, a lot of monies. So they basically promote more about relatively large reactors at this moment, so fast reactors and high temperature reactors. And SMRs, probably government think it is kind of matter of the industry, not like Korea support very much government, like that style. And then in addition to this kind of research, lifetime extension of existing reactors and advanced reactors and R&D, Japan had to manage many things. So for example, spent nuclear fuel management. So storage facility for spent nuclear fuel, on-site dry storage, and off-site interim storage. So from now, Japan also generates many fuels, spent fuels, so we have to extend. And plutonium balance, this one is always one of the constraints. So Japan already accumulated plutonium that can be used for weapon, in some sense, up to 47 tons. It's huge. Only Japan accumulated without nuclear weapon. So then Japan always have to explain how to use plutonium to persuade the USA. And then this is why Japan probably think fast reactor is very important, because fast reactor we use plutonium, like such fuel cycle. And also Japan has a plan to use MOX fuel, not to go to including plutonium. So in the plan, by 2030, 12 light water reactors include MOX, they start. And of course, high-level waste management, particularly the site selection is very important. And dismantling and decommissioning of reactors is also very important because we have many, many decommissioned reactors. So the largest one is the damaged reactor at Fukushima. We have 4 highly damaged and 2 not damaged, but there. And other 18 reactors, so many old reactors, at the time of Fukushima accident, the closure of the old reactors, many of them decided to decommission. And supply chain maintenance, it's very difficult because we have no new build. So this one is very many challenges. But these challenges is also kind of opportunities. So they have some maybe business opportunities around there because Japan has many things to do. And then, so about the opportunity for international cooperation, because this dialogue is related, so maybe SMR development for Japanese perspective, it's maybe kind of opportunity. Because Japan government does not very support SMR. So maybe Japan want to have some regional cooperation. So if we can make some regional startup companies, maybe Japan doesn't want to have Korean SMR, but if it's kind of Korea-Japan companies SMR, maybe we can have. So such thing may happen. And also regional stable supply chain, also it's very helpful. Maybe Japanese government companies want to have some job to maintain Japanese, the technology. And human resource development is always also important. So we may have some course between some top universities like us and the University of Tokyo and Tsinghua University, etc., to cultivate entrepreneurship spirit of the regional business, SMR. And also microreactors, today we didn't talk, but it's very important because we can deploy very, very small nuclear reactors to immediately provide some electricity at natural disaster damaged area. So Taiwan, Japan, we have many disasters. So this kind of thing also very important. And then, but factor we have to consider is cultural difference. I always very feel cultural difference. As you see, Japan, very, very stable in policy. So for example, SFR, Japan actually failed in Monju, prototype reactor, but Japan still working on the demonstration reactor. So Japan policy is very, very long lasting. But Korean policy very changing, for example. So Taiwan policy, so such things also we should consider to really consider real cooperation. Yeah, thank you very much.
Thank you very much for detailing about the challenge of the Japanese nuclear policy and also the potential for the collaboration, the potential difficulty of the collaboration. Okay, so sorry for bad timekeeping, and now we'd like to have a short break, but limited time, maybe 10 minutes? Okay. So we'd like to begin the next session at 11:15 sharp. Okay, please have a short break. Yeah. Okay, so we'd like to go into the next part of our session. It will be about the energy storage and the distribution. So we have Dr. Kim, the engineer and the general manager from the Korean Electric Power Corporation. So, yeah, Dr. Kim, yes, yeah, please, floor is yours. Yeah.
Okay, good morning, ladies and gentlemen. I'm Hyunjin Kim, the general manager of the grid planning department in Korea Electric Power Corporation. First, I would like to express my gratitude to the organizers for providing me with this opportunity to share some insights on the current major issues in the power grid and the response strategies that we are currently facing. As you may know from recent media reports, stable power supply is a major challenge for national energy security. In addition, with the growing interest and use of AI, the power demand for AI is rapidly increasing. As Professor Lee said before, in the past, searching information through Google was mainly used, but now asking questions to ChatGPT is being used more frequently. And some researchers say that it consumes much more electricity than Google searches. For example, OpenAI ChatGPT uses 3 watt-hour of power for a question, which is 10 times the amount of power used by a Google search. The increasing demand for power requires stable power resources, and this requires the construction of a large number of power grids that can stably deliver the electricity. I may not be able to provide the answers to today's issues, but I hope that through this dialogue, we can work together to find out the best solution. Okay, energy sources are transitioning from traditional fossil fuels to renewable energy. And not only producing energy, but also storing and efficiently distributing it is emerging as an important issue. This is a forecast of domestic peak power demand and renewable energy. The peak demand in the domestic market is expected to increase rapidly by 2038. The power demand for semiconductors and data centers in 2030 is expected to more than double compared to 2023. Renewable energy is expected to increase approximately 116 gigawatts by 2038. As you can see this, the demand for electricity is concentrated in the metropolitan area. Additionally, all the new demand for advanced industries such as semiconductor clusters and data centers is also planned for the metropolitan area. So the concentration of demand in the metropolitan area is expected to become more severe in the future. Due to the geographical characteristics of our country, the potential for renewable energy is mainly concentrated along the coast and in the southern region. On this page, I will explain the energy self-sufficiency rate, which is an index that compares the amount of electricity generated with the amount of electricity demanded in each region. If you look at the actual energy self-sufficiency rate by region in 2023, we can see that the metropolitan area has a very low rate because the demand is greater than the generation. On the other hand, non-metropolitan area have a large rate. According to the current status of data center power supply application submitted to KEPCO in 2023, 61% of the total, which is about 10.5 gigawatt, is being applied for in the metropolitan area. As shown in the diagram on the right, according to the 10th basic plan for electric power supply and demand, the total renewable energy will be about 108 megawatt in 2036. And about 75% of the total is expected to be installed in Honam and Yeongnam. By checking the long-term planning for power transmission and distribution facilities established by KEPCO, we can predict this phenomenon. The 10th investment cost increased drastically 56.5 trillion won, which is 2.1 times the amount comparing with the ACE plan. Through simple trend analysis, it is estimated that the reinforcement demand for the power grid to achieve carbon neutrality in 2050 will be approximately 81,500 circuit kilometers, which is about 2.3 times the scale compared to the end of 2022. Let's take a look at the constructions for building power grid in South Korea. As resident awareness of property rights and environmental rights increase, they fundamentally oppose the installation and operation of power facilities near their living area. On the left table, you can see several cases where construction projects have been delayed, resulting in failing to meet the target date for completion of the necessary power facilities to meet the initial demand increase and new generators. Lack of power grids can lead to instability in the operation of power system in the future. And if this situation becomes severe, consumers may face restrictions on stable electricity use. Okay, given the challenges that the power grid is currently facing, I will now discuss potential strategies for addressing these issues. The demand for new power grids is increasing rapidly, but the construction of these networks is being delayed due to low public acceptance. In other words, the traditional power grid system, which solely relied on power grid construction, is now facing limitation. In response, we must explore ways to optimize the grid through demand and renewable energy dispersion, establish systems for timely grid construction, and maximize the use of existing infrastructure, such as energy storage system, flexible alternating current transmission systems, and virtual power plants, etc. To respond to new risks and achieve stable power grid operations, we need to innovate beyond the limitation of the existing power grid system. Okay, now I will discuss the response strategies of the government and KEPCO. The government has established a joint task force with academia, research institutes, and industry to identify challenge in the power grid and discuss response strategies, resulting in the formulation of the power grid innovation measures, which were announced in December of last year. And KEPCO has established a task force organization to implement the execution strategies for a total of 55 tasks in 5 divisions, in addition to the existing government power system innovation measures in January of this year. To increase the acceptance of renewable energy, it is required to secure synchronous condensers and energy storage devices. According to the government's 10th Basic Plan for electricity supply and demand, it is necessary to secure ultra-responsive resources for stable operation of the power grid. And this includes short-term resources to ensure stable frequency, real-time power supply and demand, and voltage stability. Finally, long-term backup facilities are required for the expansion of renewable energy acceptance. Okay, we have prepared the following plan to optimize the construction of power networks tailored to regional new demand and supply plans and issues. In the metropolitan area, where there is a significant increase in demand and power grid congestion, we plan to implement reasonable power grid reinforcement. In the Yeongdong and Yeongnam region, there are many difficulties in transporting power due to delays in transmission line construction. In response, we are currently implementing measures to increase the capacity and reinforce some existing lines. In the Honam region, where renewable energy is concentrated and the continued operation of a nuclear power plant has been decided. So we are promoting a plan to directly link the access of power to the metropolitan area. On the demand side, we plan to introduce a system called Electric Power System Impact Assessment for businesses that plan to use a certain amount of electricity or more in order to promote demand dispersion. On the generation side, we plan to promote supply dispersion by designating power system management substations that are at full capacity for receiving power in regions such as 전라남도, 전라북도, and Donghae, where power generation control may frequently occur, and by restricting power generation permits by taking into account grid conditions when levying power generation permits. At the same time, we plan to manage a regional electric power system consultative committee under the government supervisions to address the saturation of capacity for accepting power generation in each region. In addition, there is a problem where the entry of later developers is hindered due to grid hogging that only reserve a power grid but do not actually engage in power generation business. This problem will be addressed by strengthening the management of transmission grid hogging to support sincere business to be connected to the power grid in a timely manner. And also, we will proactively establish facility plans at the project permitting stage to ensure that a construction period that can respond to contingencies such as complaints and lawsuits is secured in advance. To this end, we plan to designate national core project by considering important factors such as the contribution to national competitiveness and the level of enhancing public benefits, as well as their urgency. We plan to designate the national backbone power grid project and enact special laws to strengthen measures such as improving permit processes and providing compensation support. In order to establish a comprehensive support system, we plan to operate the National Backbone Power Grid Expansion Committee under the Prime Minister Office, expand the agenda items for permit and apply special provisions for environmental impact assessment, among other measures. Additionally, in order to minimize damage to the public, we plan to implement differentiated compensation and support for landowners, such as incentives for early agreement, and for residents who have been affected, such as support for renewable energy projects. In order to strengthen cooperation with related organizations and enhance public acceptance of power facilities, we are implementing a system of deeming consultation concluded for the application and approval of implementation plans. Also, we have decided to legalize the operation of the siting selection committee in order to ensure transparent selection of the sites, and have completed the revision of the Power Development Promotion Law and subordinate statute for this purpose. In addition, through legislative proposals in September 2023, we are promoting the reflection of the Consumer Price Index on regional support project cost. Okay, before the construction of the transmission line, we expect to maximize the use of existing facilities by improving system operation method, changing the configuration of existing power lines, and applying grid stabilization energy storage system, and utilizing flexible alternating current transmission system. In addition to the technical aspect, we also plan to implement NWAS strategies from a regulatory perspective, such as the customer participation load blocking system. Okay, in the era of great energy transition, securing the power grid is an urgent task for ensuring national competitiveness. As I have introduced a variety of strategies, this is the time when the attention and cooperation of the nation, local government, and the people are needed to implement them. Our KEPCO will also do our best to secure the power grid in order to meet the national energy policy and provide stable power supply to the customers. Thank you for your attention.
Thank you very much for Dr. Kim for giving us an overview of the grid issues and response strategy in the context of Korea. Okay, so we'd like to move to the discussion part. So maybe the seat is set here. So the discussant, please come to the front so that we can begin the discussion. Okay, so in this session we heard about the renewable energy and also the nuclear issue of the three countries in Korea, Taiwan, and Japan, and also the grid issue, especially focusing on the Korea. So maybe we'd like to have a cross-cutting discussion. Maybe one of the focus potentially might be the potential for the international cooperation among the three countries. Already some of the ideas are raised in the presentation, but how do you think about that? Those kind of things can be discussed. Then after that, we'd like to get some question or comments from the audience. So maybe I'd like to ask first Professor Jong Lee to give us a comment. You are the only, how to say, two of us are already presented, so you have an overall view. So we'd like to ask you to give us a cross-cutting comment and some question first. Yeah.
Actually, I'm a discussant today, but I'm kind of replacement. You know, we couldn't find the proper discussant. So anyway, before I'm talking about the kind of cooperation among the three countries, I'd like to review some situation in Korea. Okay, some of them already mentioned in the presentation, but anyway, so demand for the electricity is projected to increase significantly with the expansion of the data centers and the construction of the semiconductor clusters driven by the diffusion of the AI. Okay, so this South Korea mirrors these trends as well. In the future, in Korea, plans are underway to construct approximately 700 new data centers and the world's largest semiconductor cluster requiring around 10 gigawatt of power in Korea. Consequently, as Professor Yoo-ho Lee pointed out, for the first time, Korean government has incorporated the demand for the AI and semiconductor in its recent working draft of the 11th National Basic Plan for the Long-Term Electricity Supply and Demand. Sorry, the plan name is quite long, but anyway, I'd like to point out this. Korea is the only country in the world, they are announcing the national plan for the electricity supply. Even though the bureaucracy is almost same as the Japan, but even Japan just announced the outlook, not the national plan. So I mean, we can easily think that if it is national plan, maybe it reduces some risk and uncertainties. But the thing is not like that. I mean, I think due to the supply plan, is announced by government. Actually, it increased the uncertainty and risk, I guess. Anyway, in this plan, the newly assessed demand of the 1.4 gigawatt from the semiconductor and 4.4 gigawatt from AI data center is not the total demand. I mean, it is just an additional demand on top of the existing demanding trend of semiconductor and AI data center. So the absolute level of the demand for those AI center and the semiconductor the factories is a lot more. Okay, so by 2038, additional demand from those facilities is estimated to reach about the 17 gigawatt, leading to a significant upward revision of the target compared to the previous government plan, 10th plan. So in order to support, so the 10th plan was announced around 2 years ago, and the 11th plan announced, this year. But even in the 10th basic plan, to support that plan, we need the additional more than 40 billion US dollars investment in just in power grid. Okay, and however, this investment will increase dramatically up to around 80 to 100 billion US dollars, which I'm not sure. Maybe it is more. So it means that the General Manager Kim just pointed out, in order to make up those uncertainties and risks from the power grid, we need the huge scale investment. Anyway, and then also the urgency addresses the imbalance of the electricity supply and demand have become more pressing. Okay, as of last year, metropolitan area means the Seoul and the Gyeonggi province have electricity self-sufficiency rate only 10% and 62% respectively. Okay. So in addition, as power-consuming facilities such as data centers and semiconductor clusters have persisted to be concentrated on the Seoul and Gyeonggi province, the regional gap in electricity and supply demand is expected to widen. So meanwhile, the electricity generated far away from Seoul and Gyeonggi provinces faces limitation in supply due to the grid saturation. So we have actually some idling power plant, far from the Seoul, not from the economic reason, just because of the limit in the power grid capacity. Okay. So moreover, the future investment and expansion of the power grid poses various challenges, including the site selection and the opposition from the local residents. Okay, so if there is a local residents opposition, then local government cannot give the license to the companies and like a KEPCO. Therefore, to alleviate those regional imbalances, it is essential to decentralize the energy demand and supply. I mean, both of them. So, as part of the demand decentralization effort, the Korean government has already implemented the power system impact assessment under the Special Act on the promotion of the distributed energy, to which I myself contributed in designing. So in case of the supply decentralization, the active use of the distributed power sources like SMRs or flexible resources like synchronous condensers and ESS can bring the supply source closer to the demand point. So this approach can reduce the need for the additional investment in grid and then alleviate the burden on the power grid and enhance the system reliability. But the most important thing in Korea is changing the market system has remained unchanged for more than 20 years. Okay? So it involves introducing the system like a real-time market, forward market, capacity market, and operating them in balanced manner. So it is not yet implemented, but we need to change our market system, in the electricity. So going forward, it is necessary to discuss continuously on how to transition to domestic electricity market system from the large scale to centralized generation to the small scale and decentralized generation. Okay, that's.
Yeah, thank you very much, Professor Lee, giving us a very important comment. And the first part, I think, focusing on the increasing demand of the data center or semiconductor industry and the AI and the energy issue. Maybe this might be the interface between the topic of the yesterday and today, and those are the closely related issues. And also the second part focusing on the decentralizing trend of the system. So that might be, meta-level big issue, combining the grid issue, which was discussed, and also the SMR issue. So thank you very much for identifying the two major issues. Okay, so now I'd like to move to the Professor Chang. You have any cross-cutting comments?
Yeah, I continue to the topic of AI and the data center. In Taiwan, just last week, Google decided to have a new data center in Taichung, in the middle of Taiwan, and at the same time, they decided to establish a 1 gigawatt solar PV for their demand. So yeah, in Taiwan, at this stage, the situation is so renewable energy is not enough because the demand side in the industry is very, very urgent, like a TSMC. TSMC is supply chain of Apple. Apple requests all the supply chain should use renewable energy. Is renewable energy 100%. So now TSMC buy almost the wind energy in Taiwan and also solar PV. And actually, I know TSMC was planning to have his own solar PV plan, but later they cancel out. So now the situation in Taiwan is so TSMC is a big buyer of the renewable energy. And how about the second tier supply chain? It's small and medium entertainment. TSMC can buy cheaper because they have quite an amount of the renewable energy. They can deal a low price. But the second tier supply chain, their price is higher. So now the situation is so in Taiwan that it's not only the policies of the government, but the demand side in the industry is very urgent. So it's also the reason why in Taiwan we need more and more renewable energy. And now besides the renewable energy, actually hydrogen is also and storage and the smart grid it must be developed at the same time and together with the development of the renewable energy in Taiwan. I think just as I mentioned in my last slide, the cooperation of the triple side actually not only the offshore wind. I think because solar PV is relatively mature, but the other, for example, hydrogen and storage, and I think our three countries can have a global view and to cooperate together, and because our competition is EU or China and America, USA, and we are if we can together and to share and cooperate. And I think it will be, in my side you can see, after 2026, the development is focused on East Asia. So it's our opportunity.
Thank you very much for the issue of the increasing demand in Taiwan case and also the international potential for the collaboration. From myself and I'm also the discussant. So the one issue which is very interesting about the increasing power demand from the data center and so on is that I'm not a specialist on that, but when I talk to the specialists on the energy and also the information technology, what seems to be an interesting implication might be it has implication for the siting issue for the data center or the manufacturing themselves. So yes, on the one hand, there is an increasing demand from specific area, manufacturing area, cluster. So there have to be a grid. That's on the one hand true. But thinking about from the other way around, maybe where the renewable energy can be produced might be the good place for siting, especially for the company with thinking about the RE100 or something like that. They have to get some the renewable energy. So siting issue has been an industrial policy issue and later environmental issue to some extent, to avoid the pollution to the human population, to the area. Siting is very important. But now, one of the important criteria for the siting include the kind of production of the renewable energies. So that seems to be a changing implication of the increasing demand. That's one thing I thought about. Concerning the potential international collaboration, as actually I discussed with Professor Chen yesterday, concerning wind, there seems to be an interesting, very potential. So Taiwan has developed the kind of a new experiment, the demonstration project, and also Japan at least has a policy to reorient more to the wind, and also there are the many projects proposed in the northern part of Japan, the Akita prefecture and so on. So there seems to be some commonality and the potential for the learning to each other. And also one of the issues might be the local industrialization rather than just technology transfer from Europe, Vestas, and so on. How to develop the kind of indigenous industry in the Asian region, maybe Korea, Japan, Taiwan, and possibly Southeast Asian countries. And also, the port is very important infrastructure for managing the wind. So the Taichung, the Professor Chan mentioned, is becoming important. And in the case of Japan, for example, there is an experiment undertaken in the Goto Island. It's a Nagasaki prefecture in the Kyushu. And they are supported by the Kitakyushu city government, who is managing the port for the industrial city. So that kind of the local manufacturing and the infrastructure, how they can be mobilized to support this kind of the new development of the wind. So it seems to be, I think, potentially one interesting topic. So do you have anything say about the potential for the international collaboration?
Okay, so the making the demand and supply point more closer to each other is a kind of binding condition in Korea already, because as I told you, the in order to connect the grid, in Korea, when demand point want to connect the grid, the company should have the power grid impact assessment. So it means that from now on, it is virtually impossible for the companies to build a new data center in the Seoul or the Gyeonggi province. So actually, Korean government, by adopting that assessment, Korean government is promoting companies to be located near to the the renewable energy sources. Okay, so that should be done. And then for the the wind power, I mean, like in your presentation material, Korea and Japan, we have we have the very big share of the PV, right, compared to the wind power, right? So, I mean, in Taiwan, I mean, the ocean wind power is well promoted, but it is not like not in Korea and Japan. But if I limit it to the discussion to the case of Korea, I mean, we have a kind of constraint to build the ocean wind power because we have kind of big, what can I say, the military tension between the South and North Korea. Okay, so if you like to build the ocean wind power, I mean the Navy and then it is a kind of military zone of the Navy. So it is very limited to build a large scale wind farm on the ocean. So I think it is not different in Taiwanese case, right? You have a kind of big conflict, right? so that is the kind of the big issue. And the other issue is that the Korea, Taiwan, and Japan. I mean the samely, we are kind of vulnerable to the earthquake and typhoon, right? We already saw the very big power break in the ocean wind power in United Kingdom, right? Because of the that break, I mean the electricity price hit the hike, right? So, but the United Kingdom case is somewhat robust compared to the Korea, Taiwan, and Japan because we are all like island countries. Korea is a peninsula, but it is blocked to the upper side by the the North Korea. So we have kind of isolated power grid, not connected to the other countries. So we actually, if we increase the ocean wind power to the large scale, and then considering our we are very vulnerable to those the earthquake or typhoons, maybe that uncertainty the risk is coming us in bigger scale compared to the U.S. And so maybe we cannot we cannot, actually persist to that kind of risk or the uncertainties.
Yeah, because about the national security, actually, yeah, maybe it's a joke. Yeah, in the Taiwan Strait, we have so many. At this moment, we have about 300 wind turbines in the Taiwan Strait. It could be the first line for the national defense because the Chinese Navy vessel that they cannot pass through the wind farm because under the wind farm they are all sea cable. So also the submarine cannot pass through. but actually, yeah, sure. Renewable energy or SMR actually is the decentralized energy. It's better for the national security. Yeah, because in the world, yeah, a decentralized energy supply maybe is more safe. Yeah.
Yeah, thank you very much. Initially, the mentioning about the power impact assessment is very interesting, and we had the environmental impact assessment, but now we have a power impact assessment. It means that that's very important part of the siting decision. So it already institutionalized, and that's a very interesting point.
They say they are promoting, but actually they are forcing.
Okay.
Not to build the
Yeah. And also the geopolitical tensions implication is interesting. Can be a target or can be a fast defense.
Renewable energy now actually we separate the electricity market and the certification market. And if you have a renewable energy source, you can sell the electricity and also you can sell the certification.
Okay.
So I think Korea and Japan and Taiwan, we are not so big like China. China in Mongolia or in Xinjiang, they have many onshore wind turbine, but it is not to the demand side because it's too far away. The cable lost too much. Yeah.
Thank you. So we have only 3 minutes left, but if any question, yes. Yeah.
Thank you so much. My question might be the elephant in the room, but I'm going to address it in anyways, and that is on the trade-off between promoting renewable energy transition on the one hand and increasing economic security on the other. And to be more specific, transition to this renewable energy is a good idea, but doing so often means that we're going to be increasing reliance on the Chinese technology and Chinese supply chains. And I wonder how the 3 governments are thinking about this. To be a little bit more specific, for example, you look at wind power, and if you want high quality, cheap software for controlling the wind turbines or looking at blades, the hardware to build this, it's really Chinese, so we're going to be relying on them increasingly. But this could potentially open us up to vulnerabilities for cyber attacks, because that's one of the reasons why, once again, the 3 governments are not using Chinese technology, right? It could increase cyber vulnerabilities. Or take solar energy, for example. You look at the market share of solar panels, and it's mostly Chinese, and if you're looking at Chinese supply chains on solar panels, it all goes to Xinjiang, and there has been various reports coming out about the state-sponsored forced labor in Xinjiang. And even if we decide that no, there's no forced labor going on in Xinjiang, that's going to put us at odds with the Western government, which has already determined that yes, this is already occurring. And then for both wind and solar, increasing economic dependence on China means that we're going to be opening ourselves up vulnerable to potential economic coercion. And I think all 3 governments had suffered economic coercion from China in recent years. And there's probably a risk in increasing dependence on a country that has a clear track record of engaging in this economic coercion on issues that's so important, such as energy, which is a critical infrastructure. So once again, I'm wondering how the 3 governments are thinking, analyzing about this trade-off between transitioning into a renewable society and de-risking from China, which seems to be occurring. Thanks.
Any response? Okay, yeah. Okay, yeah.
Okay. Yeah, increasing the share of the renewable energy is kind of opposite to the improving the energy security, as you said, because when the share of the renewable energy increases, the stability of the power grid and management become more vulnerable, right? So and on top of that, as you said, we are, especially in the PV solar panel, we are very much depending on the production of the Chinese companies, right? However, in Korea also, even though it is more expensive than the Chinese one, but we have the kind of the industry ecosystem in that supply chain. So maybe it can, maybe we can support the other countries, if there is a kind of the problem happens in the supply chain with the China, maybe it can be implemented. But for the the wind turbine or the the ocean wind farm, dependency on the the Chinese companies is comparably small, right, compared to the PV panel. And as well, I want to also comment on that actually the production process of the PV panel is very much similar to that of the semiconductor. So all three countries has the kind of technological potential to increase and improve the those production of the PV panel if there is a kind of security problem. But economically, it is. If there is no security problem, economic perspective, it is okay to use the Chinese panel. But if there is some crisis like supply chain crisis, then I think all three countries have the potential to produce their own panels, and then.
Yeah. In Taiwan, actually, at this moment, it's not allowed to use the made in China, not only the solar PV, but also the wind turbine. So it's also the reason why we have the localization requirement. And actually, we already have seen in many Hollywood movie, if it's a hacker into the grid, you can stop your electricity grid. So it's also a very important national security. So I think it's similar to the communication device.
For the cyber tech, every power plant in Korea, they are operating the kind of closed network. Okay, it is not connected to for the operation network, they are connected to the external network. Okay, so for the PV and the wind farm, that can be operated in the same way, I guess.
Yeah, I don't have anything to add, but I basically agree with the previous discussion that relatively wind might be more, not relying so much for China. But even in the case of a PV, for example, the critical mineral and so on, it's true that there is a trade-off, as was mentioned. But some of the trade-off can be solved through finding another source or the technical innovation and so on. So the trade-off is not a kind of absolute thing. It can be a manageable thing. That's also have to be think about. Okay, so yes,
So I would like to add some more comments on the vulnerability of wind power to natural disasters, as Professor Kim mentioned. You mentioned the less deployment of wind power in Japan might be due to the large capital investment and long construction requirement. But I think one of the reasons might be Japan is vulnerable to natural disasters, typhoon, earthquake, and in addition, we have a tsunami risk. I think in Taiwan has the same earthquake risk and typhoon risk, but they are fortunately free from tsunami risk. And I think your floating tripod, floating wind turbine might be safe from the earthquake. It is very stable on the wave condition. But the problem of wind power is the variability. The power and the voltage is varying. And in semiconductor factories, very stable voltage is required. So I think even though you can generate large capacity of electricity, you would still need large capacity of ESS. So I think in order to increase the share of renewables, including wind power, the development of various types of energy storage system is essential, including the battery type 1 and also other thermal or mechanical type ones. So my suggestion for the collaboration of three countries is to work together on ESS. I think it will help all three countries a lot.
Yeah, thank you very much for your suggestion. So maybe there might be many things to be discussed, but I think it's time, so we'd like to close this session. So thank you very much for the discussant and also the presenter, and then also the participant for paying attention to this issue. Thank you very much. Now I'd like to mic back to the professor.
Say a few words to close out the session. Thank you very much, Professor Ju Young-chang and Jian-Gyu present, and all the participants for this conference. When we were planning this conference, we had some specific objectives. First is, of course, fostering collaboration and sharing knowledge and expertise. And, you know, not only in areas of semiconductors, AI and energy, I think generally, based on country-specific ideas, innovation, and regulatory and policy development, I think we achieved that objective. And also we were trying to address regional and global issues or vulnerabilities, especially issues concerning global supply chain. On that specific objective, I think we more or less had quite a few ideas and suggestions that should help us down the road. And also we, you know, examine some of policy developments and regulatory discussions. And of course, all these industries, especially energy, is, you know, quite a regulatory industry. So there are a lot of government-related issues on government's action and their limitations. And I think we also had very good discussions on that. And based on all these different objectives, I think we basically set a precedent for the future. We know that we will work continuously with DSET Taiwan from now on, and we hope to build on this to work more with our Japanese counterparts as well. And I thank you again for taking your valuable time off to come to Korea. The weather hasn't really helped, but the extreme weather didn't happen, so that's a positive. And hopefully we'll hope to see you either in Seoul or, you know, or Tokyo or in Taipei, and hope you have a safe journey back home. Thank you again.